In today's video, we're going to understand ship stability in a very simple and practical way.
When we look at a ship, especially a huge cargo ship or passenger vessel, one question naturally comes to mind. How does something so massive float safely and remain upright in water? And how does it stay balanced even when there are waves, wind, cargo movement, and changing sea conditions? The answer lies in ship stability. In this video, we will understand what ship stability means, why it is important, and the key concepts behind it, like center of gravity, center of buoyancy, metacenter, and metacentric height. So let's begin. Ship stability is the ability of a ship to return to its original upright position after it has been tilted by an external force. That force could be wind, waves, turning, uneven loading, or shifting cargo. In simple terms, ship stability means the ship's ability to maintain balance. If a ship tilts and then comes back upright, it is stable. If it tilts and cannot return properly, or continues to lean further, then it may be unstable.
This is why ship stability is one of the most important topics in ship design and marine safety.
To understand stability, we first need to understand the two main forces acting on a floating ship. The first force is weight. The entire weight of the ship acts vertically downward through a point called the center of gravity, or as we call it, G. The second force is buoyancy. Buoyancy is the upward force exerted by water on the ship, and it acts through a point called the center of buoyancy, or B. So the ship's weight acts downward through G, and the buoyant force acts upward through B. When the ship is floating upright, these two forces are aligned in the same vertical line, and the ship remains balanced. When a ship tilts, the underwater volume changes shape. Because of this, the center of buoyancy shifts sideways. The weight still acts downward through the center of gravity, but the buoyant force now acts upward through a new shifted position of the center of buoyancy. This creates a turning effect. Depending on how these forces act, the ship may return upright, it can incline further, or may even turn upside down, which I will explain in next chapter. This is the basic principle behind ship stability. Now let us come to one of the most important concepts in ship stability, the metacenter. The metacenter is a point used to judge the stability of a ship when it is given a small angle of heel. When the ship is upright, buoyancy acts upward through the center of buoyancy. But when the ship tilts slightly, the underwater shape changes, and the center of buoyancy moves to a new position. If we draw a vertical line upward through this new center of buoyancy, that line cuts the ship's original vertical center line at a point. That point is called the metacenter, or M. In simple words, the metacenter is the point where the new line of buoyancy intersects the original vertical line of the ship after a small tilt. This point is very important because it helps us decide whether the ship is stable or unstable. If the metacenter lies above the center of gravity, the ship tends to return upright. If the metacenter lies below the center of gravity, the ship tends to heel further and may become unstable. So, the metacenter acts like a reference point for initial stability. The distance between the center of gravity G and the metacenter M is called GM, or metacentric height. This distance tells us about the initial stability of the ship. If M is above G, GM is positive and the ship is stable. If G is above M, GM is negative and the ship is unstable. So, positive GM means the ship has restoring ability. while negative GM means the ship is in danger of overturning. This is why GM is one of the most important values in ship stability.
Having a positive GM is important, but that does not mean a very high GM is always good. If the GM is very high, the ship is called a stiff ship.
A stiff ship returns to the upright position very quickly, but may roll sharply and violently. This can be uncomfortable for crew and passengers and may cause cargo shift. If GM is small but positive, the ship is called a tender ship. A tender ship rolls gently and is comfortable and stable. But if GM becomes too small, 0 or negative, the ship may become unsafe. So in practice, aim for a suitable GM, neither too high nor too low. A ship's center of gravity is controlled by carefully distributing cargo, ballast, fuel, and stores. Stowing heavy cargo low in the ship lowers the center of gravity and generally increases the metacentric height, GM, improving initial stability. Conversely, placing heavy cargo on deck raises the center of gravity and reduces GM, making the ship less stable. Onboard loading computers, commonly called lodicators, are used by ship's officers to calculate and monitor stability, drafts, trim, list, GM, and hull strength limits. They help officers plan and verify loading safely, although the final responsibility remains with the ship's officers. When a ship has slack tanks, or partially filled tanks, the liquid can move freely from side to side as the ship heels. This shifting liquid creates free surface effect, which raises the virtual center of gravity and reduces the ship's overall stability. Free surface effect increases as the tank's width increases. When preparing a cargo plan, free surface effect must be taken into account. If the GM is too less, free surface effect can further make it negative. To summarize, the distance between G and M is called GM, and it tells us about the ship's initial stability. A positive GM means ship is stable, while a negative GM means ship is unstable. Stability is affected by cargo loading, ballast, free surface effect, and external forces.
That brings us to end of this video. Our paid membership can offer you more of such videos. Do join us with paid membership and do not forget to subscribe.